So this video is part of a course on food physics. The video relates to the porous media framework that is a part of the theory section of that course. And this subsection belongs to the governing equations for deformation or the solid mechanics aspects. So all of these are the solid mechanics aspects. The immediate preceding videos are the development of the equations for poromechanics, and then immediate follow-up is a discussion on how we can obtain permanent deformation. In a food process, many different driving forces that lead to deformation of the food product can act simultaneously. Two of the common ones are gas pressure that causes it to expand and moisture loss that lead to shrinkage. So here in bread baking, you can have expansion due to gas pressure from either evaporation or CO2 generation inside the bread. And simultaneously, near the surface in particular, you can have shrinkage due to moisture loss. So both of these happen simultaneously, and it is important to see how we can include these in nice, clean, mechanistic ways. When multiple driving forces act simultaneously, we include their effect separately using the deformation gradient as follows. So when the deformation is small, like in this case, in a frying process, let's say, especially early stages of frying, then the deformation gradients are additive. So the F due to, let's say, moisture change and F due to temperature, they are added together. Whereas in a large deformation case, like this one in bread baking, then they're multiplicative. So the deformation gradient is obtained by multiplying the effects of moisture, effects of temperature, and of course the elastic deformation. So diagrammatically, on the left, we can look at things this way. So first, let's say we start from a state of A, and then due to temperature change alone, just due to thermal expansion, just temperature changes, it goes to the state B, and so this is totally due to just thermal expansion. Next, we can think of volume change due to moisture change. So the deformation due to moisture loss. In this case, of course, it will be shrinking. And so that is the second effect. And then, of course, finally, we have the consideration of the mechanical deformation. That's the F elastic, and that's the elastic nature of the food. And so that takes us to the state D. So the total deformation from A to D it's really going through these three steps. That's kind of what's going on in these equations here for F, the deformation gradient. Since all deformations act simultaneously, for large deformation, by multiplying the F's, we get the total effect. And for small deformation, we get it by adding the three individual effects. So let's spend a little more time on how we study the effects of different driving forces simultaneously. So we think of a simple situation here where a potato, uh, the strip is constrained between two um, ends, and let's say after that, we know for sure if we dry this potato, then it's going to shrink, or it will try to shrink. But because it's constrained at both ends, it's going to develop strain and therefore stresses in the material. Likewise, even the temperature change of this will cause some. So if we include these effects, temperature and moisture, simultaneously, what does it look like? That's what we just studied. So they are included this way. The thermal effect on the deformation gradient and the moisture effect, they are multiplied with the elastic effect, of course, is there, and this is written in a tensorial form. So qualitatively speaking, then, we can think of it this way, very qualitatively, that the total deformation is temperature-driven deformation times moisture-driven deformation times the elastic deformation. And going further, so for this example that we're just studying, the temperature-driven deformation is there and moisture-driven deformation is there. So let's consider an example of potato drying. So in potato drying, this temperature-driven deformation is probably going to be small. Nobody has done detailed studies, but it's most likely to be true in comparison with moisture-driven deformation. So this is ignored not just in drying, in almost all studies that I am aware of, temperature-driven deformation is ignored. We do have the moisture-driven deformation, and the interesting part of this moisture-driven deformation is we enforce it. We don't give it a choice. So we say volume change is equal to moisture lost. So this part of it is enforced. Elastic deformation, on the other hand, is what the final effect, the final result is going to be. So this is how we include multiple multiple driving forces in case of large deformation. Likewise, for small deformation, these are added together as said in the previous slide. So here are two more examples of moisture loss as the driving force leading to shrinkage. So one is what we already discussed, that's the drying of a potato. The other one would be meat cooking, where we think more in terms of a swelling pressure driven moisture loss, whereas this one is capillarity driven. So these are two different mechanisms, but the moisture loss and then related deformation is treated the same way. It is enforced through the deformation gradient. So the moisture loss is volumetric and it is enforced through the deformation gradient. The other type of driving force, that's the gas pressure that we talked more in the previous video, that is treated as a load. So the liquid moisture loss and related shrinkage and gas pressure driven expansion, they are treated differently in the formulation. So this is an extremely important slide because here we talk about the multiple driving forces. So the two that we spend time talking, one is gas pressure driven deformation and the other one is shrinkage due to water loss or volume gain due to water gain. Uh, that how are these two types incorporated simultaneously in the final governing equation? So let's look at it slowly. So to start with, we see that this is the equation of equilibrium that we had derived, and the pore fluid pressure. So this simply says that the stress, the average stress in the solid is related to the fluid pressure, the pore fluid pressure. Now the fluid can be water or it can be gas. So the pore, the fluid pressure can be written as a weighted average of the pressure in the liquid phase and the pressure in the gas phase, weighted by the saturations. Okay. So now I bring this guy to the other side and I write this one that has the effective solid stress combined with the contribution from water pressure or the stress equivalent of that. And on the right side we have the gas pressure only. Okay, so this same equation is written differently. Now here is an interesting part. So we combine these two and call it this sigma prime effective. It was already averaged and it was already some sort of a effective because it was over the effective area. But what this effective means is it's combining the solid part with the liquid effect. So this has a different meaning, and so in terms of this combined solid plus liquid kind of a stress, we have this equation here, this one. Okay, and the right hand side, the gas pressure is the driving force. Okay, so this sigma effective includes solid and liquid water contributions. Again, just repeating what I said earlier. So if I think of bread baking, then the expansion due to evaporation and gas pressure is going to be included here. Whereas the moisture, the shrinkage due to moisture loss, that's the moisture change contribution, that is going to be included here. So this is the most critical part, that we are incorporating both the moisture driven deformation but the gas pressure driven deformation, but they're being done in slightly different ways in terms of formulation. The moisture one is here inside and the gas pressure is here as a load. So moving along, this sigma bar effective, I can change it, and I need to change it for computational reasons. We change this Cauchy stress to PK2, which is the Piola-Kirchhoff stress. And that's just a transformation. So we haven't done anything. It's just this stress transformed into this other stress, and now we plug in this part in my governing equation. Okay, so doing that, so this is the part that I plugged in, I get pretty much the final equation. So in this equation now I am using the term S effective to kind of, it's probably non-standard, but I am using it to make sure we realize that this stress S includes, it's not just solid plus the liquid water effect. So that's the stress. And so this equation now includes, this equation includes both the effects of gas, that's right here, but also the liquid water effect. So how is it the liquid water effect? That is through this F. So we already discussed F, when we ignore any kind of temperature related shrinkage effect, then F is F elastic times F due to moisture, deformation gradient due to moisture. And deformation gradient due to moisture is simply the volume change. And here in this equation we're basically saying the volume change that is going to be enforced is because of loss of water. That's how you derive this equation. It's simply a relationship between the new volume and the old volume, and the change is only due to the change in volume of the water lost. But this part is enforced, so this is given. So if you lose water, then how much you change FM, that is given, it is enforced. So then if we plug F back in here, then the what we would be solving for is this eventually the F elastic, and we will get the deformation this way. So this is my final equation in the most general form, that includes gas pressure driven deformation and the liquid water driven deformation. So in this very last slide, I want to relate this equation that we just derived to a few other driving forces using additional examples from transport that we have done earlier in the transport module. So in transport module we have discussed these modes of transport, and I want to make sure I link those modes of transport to these driving forces for deformation. So the four pressures of liquid water that we talked about is four contributions to water pressure or gas pressure, capillary pressure, swelling pressure, and gravity, and they lead to transport of water. But these effects, these four effects, are included in the final equation a little bit differently, as we already saw. So let me just repeat. Then this gas pressure effect, and in an analogous way this gravity effect would be included in the body force or the load on the right hand side, whereas the capillary pressure related deformation and swelling pressure related deformation, they will have this strain that is enforced from moisture change in here, and those strain enforced come through the deformation gradient, and the strain that would be enforced is, it says that the volumetric change in these would be equal to the moisture change. So that part is enforced. So that is done for both capillary pressure related movement of water and swelling pressure related movement of water. So this concludes the development of the governing equation for poromechanics that would be used to compute deformation in a food process, where multiple driving forces like loss of water and relating shrinkage, or uh, expansion due to gas pressure, they're both included.